Recording has started.
Okay, so it's that time. Let's go through some of these graphs off the worksheet. I realize you may not have had time to graph all 10 of them. But let's take a look and see what you have done so far. Number one, we actually already did together. Y equals 3x minus 2. On the graph, that's going to look something like this. It's going to be a line. In fact, I'm going to crunch this in a little tighter. Something like that. Number two, if y equals 6 minus x. Well, this one also is a line. Looks something like that. It goes up through here at y equals 6 and over here at x equals 6. So the first two off the worksheet were lines. Number 3, y equals x squared plus 2x plus 1. This one doesn't work out quite as easily. So let's see here. Gives us a parabola, looks something like that. Number 4. So for number 3, that's another one where you'd pick a few points, put them on the graph, and then use the graph to decide where I need more points to plot to figure out what that's going to look like. Number 4 is actually a very tricky one. Y equals the square root of x plus 6. Let me try that again. Looks something like this. Now you'll notice all the other graphs we've made here, I put arrowheads on both ends. Because all three of those first three graphs continue to go in either direction. I could extend those lines and keep going with them. This one here does not have an arrow on that end, because that point there corresponds to x equals negative 6. If I put negative 6 in for x, I have the square root of negative 6 plus 6, which is 0. The square root of 0 is 0. That's fine. But if I put anything smaller for x, like negative 7, well, negative 7 plus 6 would be negative 1. And the square root of negative 1 cannot be done. So x cannot be smaller than negative 6 there. So it's what we call limits on the domain. We're not going to get into function notation or anything like that in this course. If this were an associate degree tech math course or a college algebra or intermediate algebra course, we'd talk about domain and range of functions. All we need to know here is that there are limits sometimes on the values we can use for x. Number 5. Y equals 3 plus 3x. Looks something like that. So that one is a line again. Arrowheads on both ends again as well. It goes on, can extend it in both directions. Number 6. Y equals 2 to the power of x. This is one that's a little tough to graph because it gets into decimals. It'll look something like this. It does continue on forever in both directions, and we'll notice as we go this way, it gets closer and closer to that x-axis, but it's never going to quite touch it. That's what's referred to as an asymptote. The graph gets closer and closer to that line, but it never actually quite touches it. It's kind of a limit on the line. The graph will approach it, but never go past it or get to it. Number 7, very similar to an example we did earlier. Y equals x to the third minus 1. That cubic curve or that S-shaped curve, looks something like that, goes through 1 below the origin, right down there. Number 8. This is a tough one to graph. Y equals 8 over x. Now, first of all, if you tried to put 0 in for x, 8 divided by 0 is an error. You cannot divide by 0. So x cannot be 0 in this equation. So the way it ends up getting graphed is going to look something like this. It's 2 curves. One is up here in the positive where x and y are both positive. And the others down here where both x and y are negative. And you notice it never goes through the y-axis here. Again, that's an asymptote again. Our graph can approach that line, but it can never cross it. X can never actually be 0. So our graph can never touch that line. There's actually a second asymptote here, the x-axis. As we go off to this direction, we get closer and closer, or if we go off to this direction, we get closer and closer. We're never actually going to touch that x-axis. Number 9. Y equals 4x squared minus 8. So this is a very narrow pointy parabola. Looks something like that. And finally, number 10. Y equals 3/4 x minus 4. It looks something like this. It forms a line. So as we look at this, first thing I want to note is that there are 4 equations here that formed lines on the graph. Those 4 equations have something in common. More specifically, the other 6 equations have things in them that those 4 that I highlighted do not have. So let's look at those 3 to start out with. Those have powers larger than 1. I didn't even say larger than, I'll say other than 1. on the variables. So this one had the power of 2, power of 3, power of 2 on the variables. Now along with that is this one here. We have that square root. The square root is actually, remember we said it's an exponent. It's the opposite of x squared. So powers or an inverse, we're going to say or a root. If I look at this one here, 2 to the power of x, and that one, the variable is in a power. And finally, this last one right here, we divided by the variable. Those three things, 4 things if you want to count a root as separate in a power, but they really are the same thing. They're exponents. Those 3 things are the 3 things that linear equations don't have. So if we look at an equation and it has any one of those 3 things, we know right away it's not going to make a line on our graph. So y equals 3x minus 2 to the third. Is that going to form a line, a graph? Well, yeah, that 2 to the third, it's a power, but it's just on a number. That's just y equals 3x minus 8. That's going to be just fine. Y equals 7 divided by x. That will not be a line because we're dividing by a variable. So no, that's not going to make a line on the graph. Y equals 16x squared minus 3. Well, there's an x squared. There's a power on my variable. That will not form a line on the graph. Y equals 8 minus 3 to the power of x. Well, the variable is in a power there. So again, going to form a line. This one here looks okay at first, but we realize we have to distribute the 3x. 3x times 2x is 6x squared. 3x times negative 5 is a negative 15x. So y equals 6x squared minus 15x. There's an x squared in there. Not going to work. This one here, y equals 8x minus 3 minus 2x. Well, the 8x minus 2x is just 6x. That's y equals 6x minus 3. That's just fine. That's going to form a line on the graph. Now, I could throw a bunch more examples up here, but I think you guys get the point. As long as we don't have any powers on the variables, other than just the normal 1. 3x is 3x to the power of 1. As long as the variable is not a power and we're not dividing by a variable, we're going to form a line on the graph. Once we know that we're going to form a line on the graph, well, then we can take some shortcuts. Let's take a look at what those shortcuts might be. Starting out with some of our most basic linear equations. Let's start out with y equals x. For y equals x, if I just made a quick table here, if x were -3, y would be -3. If x were 0, y would be 0. If x were +3, y would be +3. So we get this line that goes corner to corner across our graph. That is the most basic linear equation we can make. Now, we've talked about building on to equations and making more complex equations. One of the things we can do is add. We have y equals x plus 2. Well, if I make a basic table here, x and y will move this over a little bit. If x were -3, -3 plus 2 would be -1. So -3, -1 would be right there. If x were 0, 0 plus 2 would be 2. So 0, 2 would be right there. If x were 3, 3 plus 2 would be 5. So 3, 5 would be right there. We see that we get a line goes across our graph at the same angle. It's just moved up 2 spots. So adding 2 to x just moves the whole graph up 2 spots. Wonder what would happen if we did y equals x minus 3. Well, if x were -3, -3 minus 3 would be -6. -3, -6 would be right there. If x were 0, 0 minus 3 would be -3, so that's right there. 0, -3. If x were 3, 3 minus 3 is 0, so we got 3, 0 right there. So again, it stays at the same angle across the graph. It just moved from the origin, it moved down 3 spots. Makes sense. Well, let's look at our other things. We've added, we've subtracted. Let's talk about multiplying. Y equals 2 times x. Well, now if x were -3, 2 times -3 would be -6. -3, -6 would be somewhere in there. If x were 0, well, 2 times 0 is still 0. So 0, 0. We're back to going through the origin again. X were +3, 2 times +3 would be +6. So +3, +6 is like that. So we get a line that's back to going through the origin, but now it's steeper on the graph. If I wanted to make one that was less steep, rather than doing y equals x divided by 3, I'm going to do this. Y equals 1/3 x. Multiplying by 1/3 and dividing by 3 give you the same effect. So if x were -3, 1/3 times -3 is a -1. The -3, -1 is right there. If x is 0, well, 1/3 times 0 is still 0. Still going through the origin there. If x were 3, 1/3 times 3 is a positive 1. So 3, 1 is right there. So we get that line much flatter, less steep going across the graph, but still through the origin. Well, so far, all of these graphs, as we move from left to right, the line goes up. How can I get one to go the other direction? Well, let's try y equals -2x. Well, if x is -3, -2 times -3 would be +6. So that'd be right there, -3, +6. X is 0, well, -2 times 0 is still 0, so still through the origin. If x were +3, -2 times +3 is a -6. So +3, -6 is like that. So we get a line that goes down as we go across the graph. Well, these are really the only two things that can change about a line on the graph. It can move up and down. Instead of starting at the origin, it can move up or down to where it starts. And we can change its angle across the graph. So if I have y equals 2x minus 3, what that is saying is instead of starting at the origin, I'm moving down 3 spots, and I'm starting 3 spots below the origin. That is the -3. The 2x is saying instead of having that 45-degree angle across the graph like this, it is saying that we go a little bit steeper. Something like that. That steepness is referred to as slope. And slope is a ratio of rise to run. Now, you might hear slope being used in terms of roof slopes. That's the exact same quantity for roof slopes, rise over run. Calculated exactly the same way. So if I look at this, this was just a 2. I have to make it a fraction. It's actually a 2 over 1. So that's saying is from that starting point, that point right here, 3 units below the origin, I rose 2 and I ran 1. That got me to the second point on that line. So we might have y equals 2/3 x plus 1. So the plus 1 is telling me from the origin, I go up 1. That's actually my first point on the graph. That's actually referred to, by the way, as a y-intercept. That's where it intersects the y-axis. Typically, it goes through at the origin, but that moves us up and down from the origin. Then, of course, the 2/3, we rise 2, run 3. So from this point that we started at, the +1, we rise 2, 1, 2, and we run 3, 1, 2, 3. That gives us our second point on the line. And we can draw our line through those 2 points, just like that. We might have y equals 3/4 x minus 3. So the -3 says from the origin, we go down 1, 2, 3. That's where our starting point is going to be. The 3/4, we're going to rise 3, run 4. So from this starting point that we defined, we rise 3, 1, 2, 3, and we run 1, 2, 3, 4. There's our second point on the line. We draw our line through those 2 points. So we might have y equals negative 1/2 x plus 2. So we start out at the positive 2. So from the origin here, we go up 1, 2. That's our starting point for that line. Now our slope is a negative 1/2. The negative always goes with the rise. So what that's saying is instead of going up 1, we go down 1. We rise negative 1. Then we run 1, 2 to get to our second point. So our line looks something like that. Now it's not always quite so straightforward. The order can get messed around a little bit. This is y equals 3 minus 2x. The number with the x is always the slope, so negative 2 here is multiplying the x. Negative 2 is the slope. That means we are starting at the positive 3. So from the origin, we go up 1, 2, 3. That is our starting point. Now the negative 2x slope always has to be a fraction. So that becomes a negative 2 over 1. So from that starting point, we go down 1, 2. That's the negative 2. We run 1. The run always goes left to right. And there's our 2 points. So we're going to draw our line through them. There we are. So y equals negative 2 plus 3/2 x. We have that negative 2 that's by itself. 3/2 is multiplying x. That's the slope. It's the number that's not multiplying x that we start with, the negative 2. So that's our starting point there, negative 2. Our slope of 3/2 x. That means we're going to rise 3. 1, 2, 3, and run 2. There's our second point. So there's the line associated with that. We may have something like this. Y plus 3 equals 1/2 x plus 1. Well, everything we've looked at so far is of the form y equals. That's the form it has to be in for graphing. It's called graphing form, or y-intercept, slope-intercept form. Well, to get this into that form, I have to get y by itself. Right now I have that plus 3 there. So I'm going to get rid of it by subtracting 3. Now remember, when we add or subtract, we must have the same name, which means when it comes to an equation, when we add or subtract, we only have to add or subtract to one piece on each side. So we subtract 3 there to get rid of the 3. That would leave us with y. On the right side, we can only subtract it from the thing that has the same name. Well, we're subtracting 3 ones. We're going to subtract them from the 1, 1. So the 1/2 x doesn't change. 1 minus 3 is a negative 2. So what we have here is y equals 1/2 x minus 2. So we start out at negative 2. 1/2 x means we're going to rise 1, run 2. There's that equation. Here we have 2y equals 3x plus 4. So we're going to have to get y by itself. Y is being multiplied by 2. So to get rid of the 2, we're going to have to divide the 2. When we multiply or divide, because we do not need the same name, that means we can do it to every digit in each number. So the 2's divide out there, leaving us with y. On the right side, we have to divide each digit by the 2, each piece by the 2. 3x divided by 2, well, we're simply going to write that as 3 over 2 times x. So we just divide the numerical part, we combine the counts. 3 divided by 2. Rather than making it 1.5, we leave it as 3 over 2 because it'll be a lot easier to do our slope that way. And then we have 4 divided by 2 is just going to be a positive 2. So we start out at the positive 2 right there is our starting point. 3 over 2 means we're going to go up 3, run 2, right there. So there's that equation. There's that line. We might have 3x plus 2y equals 4. Well, we have to do a lot more rearranging, and we need that y equals. So first we got to get rid of the 3x. I'm going to subtract 3x from both sides. So that 3x is gone. I'm left with 2y there. This is why we did those literal equations last week, where it was all letters, all variables. 4 minus 3x, we really can't combine that. So that's just going to be left as 4 minus 3x. Now we have to get rid of the 2. We're going to divide by 2. So that 2 is gone. We have to divide every digit on the other side. So 4 divided by 2 is just 2. Negative 3x divided by 2, we're just going to make that negative 3 over 2 times x. So we just treat that division problem as a fraction. Negative 3x divided by 2 is just negative 3 divided by 2, or negative 3 over 2, and then still times x. So here we're going to start at positive 2. That's right there. And then the negative 3 over 2, we're going to go down 3 over 2. Get to that second point. And there's our line. For right now, I think you've looked at enough. Let's give you guys some homework to see what you guys can do as far as graphing. So in the big book, we're going to start out page 464 through 465. Exercise 16.2. Page 466. Exercise 16.3. And page 467. Exercise 16.4. We've got about 13 minutes left for you to get started on those if you'd like. We will look at these a little bit more tomorrow, and we'll pick up from there. So if you want